The last video we had created all the data that the parameter optimizer tool needs in order to find the parameters. So what we'll do in this video will be just to press run and see how the program starts to iterate. So just press run here or either the play button, and it will just start optimizing. If you go to the second tab, conversions, you will see the evolution of the parameters, and in the third one, the results, you will see the comparison between experimental and model data. You can see the parameters here. Because it's the first iteration, you're not seeing the evolution of them, but here you have each and all of the parameters that we defined in the circuit file. T2, TB, RSM, and so on. Here you have the error. This error is a measurement of the average error in the between experiment and models. If you go to the results tab, you can see the comparison between experimental and models. You can see here, let's make it bigger. Blue one is experimental data. You can see this is a static test, and this was the dynamic one. That, if you remember, it looks similar to the one I did in Paint. And the red curve is the initial guess. With the initial parameters you set here in the wizard, you get this response. And now the algorithm will just try to find better parameters, so the curve will be closer and closer to the blue one. So we were saying before here, this error is the average error. The way it works is like this. It will go to the first curve, it will take all the points, and it will calculate the y vertical error, which is the same as the area between both curves. It will do it also in absolute value, so if this curve goes down, it doesn't decrease, as it doesn't make sense. And it will also scale each point by the experimental data. This is important because otherwise, you need it in order to get an average error, but also then this error will be added to this error and to this error. And if data is not scaled by, for example, dividing just by the experimental one, when you add this error plus this error, okay, these one are similar because it's 1000 here, 1000 something here. But for example, if you have one graph, or you have 1000 volts, another graph that has, I don't know, 20. When you add the errors, the graph with 20 will not matter at all. And the thing is, both should matter the same, not because one has bigger values should matter more or less. So that's why you scale them. This is all done automatically by the tool. And you can also set importance for the graphs in case you really need it. Like usually if you use the default settings, it should be okay, but for example, let's say you care really a lot more about the dynamic response than the static one. So for example, you could say this curve has a weight of 1, let's say, as a reference. This one has 1, this one has 1. In total there are 3 curves, each curve matters the same, 33%. Okay. But for example, you could say, no, I want dynamic ones to matter more than this one. So for example, you could say this voltage curve matters 2, this matters 2, and this is default to 1. So these two combined would matter 4/5 of the total error. So the algorithm will always try to optimize more these curves than this one, since an error here is would be more present in the total error that is used. You can see here, you can barely see, but you can see during the iterations. This is fmincon. What it's doing is, since it's a gradient-based method, it's perturbing each parameter a little bit. It does it with the default settings I have set. You can change in the code, but they are mostly, for most cases, okay. It makes first a negative change and then a positive one. It's usually better than just doing one positive or one negative, since this way you have somehow you can calculate an average gradient. It's usually better this way because it's more stable. Let's say you are in the these parameters should not be changed anymore. If you go up, of course it will say the error has, for example, increased, so you say then you will go down, but no, This parameter is already optimized, it shouldn't change. So when you do gradient both ways, if the change is small, it's more or less symmetrical, so it will tend to stay in the same place as it should. So it's something you can disable through the settings inside the code, but it's not advised to do so. But you will also gain a speed, like it will take let's say more or less half the time to perform. So you can actually experiment with that, something you can play with. If you want to change it, you have to go to the main app. There's a lot of code here. It's just easier, you press Ctrl F, fmincon. Okay, here we are. Here you have the solvers. This is fmincon, and basically you have here the options, and it's saying here use fmincon as a solver, and use 1% change. If you go here, you can see this here is 1% of 1 to the -7. If you put it 5, it will be 5%, and so on. The thing is, in theory, you should put a really small value, like for example 1 to the power of -6. But the problem is that optimization problems are usually, I mean, they can solve a lot of different problems, but those small values are more appropriate, like for symbolic problems where you have functions. But because this has experimental data that has noise, for example, you can see here small ripple. If you put a really small differential relative step, the problem is that maybe you're not really getting what's going on. Like you change so little the parameter that the small ripple is perturbing your measurement of the error, and you think that increasing one parameter is helping, while it's doing the opposite, for example. So it's good to put a value bigger than the recommended, and 1 to the power of -2 to 5 to the power of -2, I would say that's a good value. Pick one between each. You will also expect let's say a better precision, maybe if you have a smaller value, so you could use just 1 or 2 to the power of -2, and if it's just not working, it's something you can try. If you see that this error graph here, you can see there's the ripple is small, so maybe you could even put it a bit bigger. But if you see it almost constant, for example, then for sure this parameter is too small, you should put it higher. Then here you have that differential type is central. This is what's doing, and it's going down and up. You can remove this and do it only go up. And what else? These are the constraints which are put automatically by the algorithm itself. This A, B, X min, X max, and all this. This is basically saving them, blah blah. And you can also change the global searches here. Again, you can change here that the percentage of change you use, if you want to use both ways, up and down. Global search here you can put, and the final version this will be a bit changed, but you can put a number of samples and stage 1 points you will use, because this is a really slow method if your simulations are slow, which is usually the case with PSpice. So this will be changed, and you will be able to change easily the number of points to use. And then you have here the genetic. To be fair, we haven't really worked that much with it, because I think it's as I said, it's really slow. And also this tool works with the genetic one, no problem, but you will not really make much sense of these graphs, because in the genetic algorithm you have generations and a lot of things that are simply not present in these graphs. So you can definitely use it, and it will work, because the data is here, it's being given to the algorithm, everything is being chosen appropriately. It will work, but first it will be slow, and second it will be harder for you to see. If you try to go to the parameter tab, you will see a lot of weird things. You will not understand anything, because information is not presented as it should, but it's still something that will work. So I don't know, it's an option I've left, because you can always use it, and it may be a good idea in certain points. I'm going to let this iteration has almost, the first iteration has almost finished. You have also to understand, is parameter change here is not considered an iteration. I mean, again, it's semantics. It doesn't matter, but yeah, so you know, because this is part of the algorithm, and you define an iteration when the algorithm performs a whole, let's say, a whole cycle, and this is part of the cycle to estimate the gradients. Here is just estimating the gradients, and then after this, the parameter will go up, then it will have all the gradients, and in the next step, it will try to predict the change. So we'll see how the error here is about 33.5%. In the next one, now it has the information, it will try to improve it. Let's see if it does so. Here at the corpse, let's see. It should go down. It usually goes down quite fast first, like for the first 2-3 iterations, and then it continues to go down, but much slower. You can see here, you know, the error has gone down now to 25% from 33%, which is fine, but still, if you leave it more time, it will go down to maybe 3%, something like that. And in certain cases, it's so good you cannot even see the difference between experimental and model. Thing is, you can see here the red one was the initial one. Now with the new parameters, you have this black, which is closer to the blue. Here you may argue it didn't change, it went to the other way. It's still a bit better. You can see the area is a bit smaller, so it's a bit better, but not much. But still, this is just the first iteration. You should leave it more time. Also, the way to understand when the algorithm has finished, I have left the default settings in most optimization algorithms except for the finite differential relative step, as I commented before the reason. I do believe that the default settings are more or less okay, because the error function has been scaled, and it will probably be, in most cases, it will be less than 1. Anyway, it will be close to between 0 and 1 most cases, since it's an error, unless your initial parameters are really far away. On the other hand, parameters, you don't see it here, but they are also scaled linearly. This parameter here teaches you, for example, the algorithm is not seeing 1 to the power of -7, it's seeing 1 initially, because all the parameters have been divided by the initial value. Again, this is always recommended in optimization problems. You don't see it, it's hidden to the user, but it's going on. And for these particular reasons, because the error function is usually less than 1, and because the parameters have been scaled, I do believe that the default settings are more or less appropriate. There's no reason to change them under these circumstances. And the results we've gotten so far prove that the results you get with these options are more or less more than adequate. So in my opinion, what you should do, like when you try to solve one of these problems, is you very carefully go to the wizard. I mean, you start with the models, you very carefully modify them, then you go to the wizard, very carefully put the data. Okay, after you finish with the data, you press run, and you do the first iteration. I mean, not even the first iteration, you just press run until you see some graphs here, and you check. The first thing you have to check is if they make sense. Like, are you doing what you have to do? This curve here is a static one, is comparing with the static one. It makes sense, but maybe you made a mistake and you're comparing this one with this one. You would see it clearly. So you have to always to know, like, does it make sense what I'm doing? And one good way is to just see the graphs by eye and see, okay, it seems to be good. Then another thing you have to consider is when is this simulation going to stop? Like, is this going to be here forever? No. With the default settings, they are more or less appropriate, but sometimes it could be a bit too slow. Like, my advice would be to just let the simulation run, and it will stop on their own. But if at some point you see the results are okay, yes, feel free to stop it. Like, there's no reason to continue. You already have everything is more or less fine. Like, why continue just to get a really small error change? Again, you can play with the default. You can play changing the default settings if you know what you're doing. I showed you like where it is in the application, so you can improve the stopping criteria. But most cases, it's better just to leave it to the program, and if at some point you think it's okay, just stop it. So we could leave this running for a few hours. I guess in, I don't know, let's say 3 hours, maybe you will get the results. And I'm going to stop it now just to show the last thing is the sport button. So I'm going to just press stop. And as I told you, the stop button may take a few seconds or minutes to stop, because you cannot stop suddenly. You have to finish the current, not iteration, let's call it a step, like you see here numbers, for example 40 to 41, like you have to continue one of those, not the full iteration, like with the as many parameters as there are. So it's finished now. You can see here stop, and it says return parameters are the ones that produce the smallest error from the ones tried. Well, this means that because the simulation has been stopped and the algorithm hasn't found a minimum, but because you stop it, and I mean you want some results, the results you will get are the ones that make the smallest error, which will be this one in this case, as you can clearly see. So you have stopped the simulation, and even if you stop it or if it's finished, then you can export the results. So just press export, create, for example, in desktop, create a folder called results R, and save, and it will auto-generate a report for you. You can see here, and it will tell you when you create run the simulation, the error from what it went, and it will also make a copy of the parameters you used in the simulation file. Let's close this and open it again to see what I mean. If you press open configuration files and you go to where you save the results, you can open this txt file that I told you here, and it has all the information from the optimization, so you can run it again. And it will also tell you the parameter evolution, initial value, final value, and percentage of change, also the graphs here, and finally also the graphs for the optimum unit found. Okay, it's maybe worth to know that if you go to the R folder, there's a lot of M files. If you examine them carefully, you will see that the data that it's in this okay, close it, but the data that it's exported again, the data that it's in these images, you have here the image, but if you want to have the whole data later for further use, or you want to modify it, you want the data exactly what you have here, if you examine these M files, you will see it's stored there. Remember, this here is the data for the curves, this one here is the data for the parameters, and here are the functions that do the plotting. So if you open the functions that do the plotting, you can actually get a feeling of how the data looks and to use it again. So thank you for your time. If there's, I hope you managed to follow the videos and understood how to use the tool. Again, as I always say, you have a help button in all the tools, so if there's something you don't understand, you can just see it there, and then you can also have access to the website where you can just check the latest updates and models, and access to the discussion. You can also go to the wiki and like contribute and add your part if you want. Okay, thank you for your time. Bye.